When it comes to trading and quoting prices for your desk, you want to produce prices efficiently and consistently. In order to do so, we typically use some sort of model from financial mathematics, and you can't disentangle the notion of stochastic calculus from those models. In this video, what we're going to do is build off of the previous video where I had discussed Ito's lemma. I had created some visualizations to help interpret Ito's lemma, and we're going to shift our focus now towards Ito integration, this idea of a stochastic integral or a random integral, and we're going to try to build off of traditional calculus. We're going to create a pretty cool visualization here so that we can understand each component of a stochastic integral, and at the end of the day, we're going to discuss why it's important, and that is in the context of pricing, and how we can go about using it to solve stochastic differential equations, which is what we're after at the end of the day. As always, I'm going to leave a link to this Jupyter notebook in the description below. I've listed out here some prerequisite QuantGuild lectures you can check out if you need some background information. All of the Jupyter notebooks for my previous lectures can be found on the QuantGuild library over on my GitHub page. But beyond that, we can go ahead and get started with this idea of the integral in the traditional sense, that is from calculus, this idea of the Riemann integral. So I'm not going to go about teaching you how to integrate a function. The integral in general is just a way to find the signed area underneath some sort of curve or function. It's also the antiderivative, so it undoes differentiation of some sort of function, or it's the inverse of the derivative operator, if you will. And what I've done here is I've just integrated analytically. That means the solution is precise, a very simple parabola from 0 to 2, and I find that the solution is going to be 2.6 repeating, or approximately 2.667. Now, analytical integration is great and the solution is precise, but it's not always possible, which is why I'm going to pivot to talking about numerical integration. We have very fast and capable computers which we can use to actually simulate and approximate the value of an integral of interest. So if I couldn't actually go about solving this integral here, I could shift my focus to numerical techniques to try to go about approximating the value, and I can get some very, very highly precise approximations. So I draw a parallel here to this idea of numerically differentiating because I've done a video on it in the past, and I definitely encourage you to check that video out. But the definition of a derivative is in this limit form where h goes to 0, but we have computers. So instead of making h close to 0, I could just make it very, very, very small. I don't have to deal with this infinitesimal. So when I say h close to 0, I'm talking about this infinitesimal in the calculus sense, but I could just make it very, very small. I could make it 0.00001, and it turns out that it will be approximately equal to the derivative value when h is small. It turns out to be a very good approximation. How is this useful? Well, it's the same idea in the definition of an integral. So you can see we have this limit in the definition of an integral as this delta x goes to 0. But instead of dealing with this delta x close to 0, I could just set delta x to be some very, very small number. And it turns out we get a very good approximation for the integral in this sense. I will digress from this idea of numerical integration in a moment, but I do want to say that we are not short of different schemes to go about numerically simulating. So this is just one scheme. I listed a pro and a con in terms of the efficiency of this approach, but we are not short of schemes to go about numerically integrating. And it's very important because this is integration in the traditional calculus sense, right? So we're not even dealing with randomness quite yet, but there are integrals that are intractable, right? We could come up with some crazy function that we can't integrate analytically, and we'll have to resort to some numerical techniques. But it's nice to know that we have a wide variety of techniques available to us, and many of them are very, very efficient and precise. So what is integration? Well, as I said, it is just going to be the signed area underneath the curve. It's also the antiderivative. It's the inverse to that derivative operator. But visually, we can see this numerical integration in action when I make this delta x value smaller. So when I make this delta x value smaller, you can see the number of rectangles increases, versus when I make it larger, the number of rectangles decrease, and the approximation gets worse and worse and worse. So remember, the actual integral value here is 2.667. The approximation here is 1. It's not a very good approximation, but as I shrink that value, gets smaller and smaller and smaller, my approximation gets better and better and better until it ultimately converges to the precise value of that integral. So that's the integral from traditional calculus. Now we need to discuss random variables and functions of random variables. It's very tempting to want to deal with a random variable in the classical sense of a deterministic integer, real number, even a complex number for that matter, but they're just not the same. A random variable is actually governed by a probability mass or density function. It's a distribution of possible outcomes that characterizes the randomness. It's a very important idea because if I say that x is normally distributed with a mean of 0 and a variance of 1, the standard normal distribution, then x doesn't take on a value. It takes on a set of possible values governed by a probability density function given here. Moreover, if we have a function of a random variable, then that function is itself a random variable. A very simple way to see this is imagine that x is a random variable. Well, we know that x doesn't take on any one value. It could take on any one of these values with varying likelihoods. So that means if I have some sort of function of x, in this case I define this function here, x squared, then how can we be certain of the value for x squared if we're uncertain of the value for x? In other words, x squared is also going to be governed by some sort of density function. It's going to be a distribution of outcomes. Therefore, the function of a random variable is also itself a random variable. Now that may sound trivial, and if it does, fantastic, but the reason why this is important is because when we introduce the stochastic Ito random integral that we're going to go about solving, we're dealing with an integral with respect to randomness. What does this mean? It means the integral isn't going to have one value associated with it. We can compute statistics, the expectation of the integral, the variance of the integral, heck, maybe even the distribution it follows. But the integral itself is a random variable. This is a very tricky idea because we're used to integrals being a value in the classical sense, right? The analytical or numerical solution is going to produce a value, not a distribution. So that's why I wanted to discuss this idea of random variables and functions of random variables, because that's all the Ito integral is. It's some sort of function of a random variable, and in that case, the outcome isn't going to be one value. It's going to be a distribution of possible values. The last part of our randomness boot camp here is going to be this idea of Brownian motion. Brownian motion is what we're going to be integrating with respect to this idea of a Brownian increment, an infinitesimally small increment in Brownian motion. And Brownian motion itself is going to be characterized by these four things. So it's almost surely continuous, has independent increments, it has this origin at 0, and the increments themselves are going to be normally distributed with a variance of the time step. This is nothing new if you've seen Brownian motion before. If you haven't seen any sort of stochastic process before, all you really need to know is if you understand the idea of a random variable, this is just going to be a collection of random variables indexed by time that are governed by these properties. It's not too difficult to grasp. Moreover, you can visualize it. So these are the increments themselves. And if you take the cumulative sum of these increments, then you get these Brownian paths, and they look quite cool. So you can see here, this is the Brownian increment. It's this noise here. And if you take the cumulative sum, then you actually get the Brownian motion process. Again, here we're dealing with randomness. So anytime we see a W sub t, this Brownian motion term, we can't treat it like a traditional mathematical object, some sort of deterministic quantity. It is itself a distribution governed by these properties. And the same is true for a differential of this, some sort of discretized increment. That is, any function involving this random variable, this Brownian motion, is itself also going to be a random variable. This is true for its differential. This is true for its integral. And again, any function involving this term. Think distribution, not deterministic quantity. This brings us to Ito's lemma. So the differential of a function involving that Brownian motion clearly has to be a distribution. There isn't one value for that differential. If there was, then it wouldn't be a random quantity, right? So Ito's lemma, what it does is it decomposes this differential of a function involving the Brownian motion into two components. Essentially, there's this drift component and this shock component. And this differs from classical calculus, and I go in depth into the reasoning why in the video on Ito's lemma, so I certainly encourage you to check that out. But essentially what we have here is just an extra term versus traditional calculus where this higher order term would actually drop out and go to zero. In stochastic calculus, it turns out due to the quadratic variation associated with the Brownian motion, infinitesimally, the quadratic variation goes to dt, leaving us with this extra term instead of this term going to zero. So not too much of a stretch there from classical calculus, but again, the reasoning why is important, so I certainly encourage you to check that previous video out. Nevertheless, we can use Ito's lemma for a variety of things. Here, we're just going to use it to observe the differential of this function of Brownian motion. So I have a simple function of Brownian motion squared. Again, it's a distribution of possible outcomes. So just like we had a bunch of different sample paths here, we're going to get a whole bunch of different sample paths here. But we are interested in this differential, that is this small change. So what I'm going to do is I'm going to compute this small change for the actual path that I simulate. I'm just going to take the difference for some sort of small time increment of the Brownian motion squared. And then I'm also going to look at the differential given by Ito's lemma. So I can use Ito's lemma. I can take the partial derivative with respect to time, partial derivative, or should say the second partial derivative with respect to Brownian motion. I could take the partial derivative with respect to Brownian motion, and I'll end up with this differential governed by Ito's lemma. And you'll see that they actually match. And they certainly should match, otherwise the differential given by Ito's lemma wouldn't be correct. But this certainly does match, right? Now, there may be some sort of approximation error that is just by the way that it's being simulated or discretized, but that's neither here nor there. Keep in mind, right, this is the differential of one trajectory. The green represents the actual difference, that is, I'm taking this function value at different points, and I'm differencing it. And then the purple path represents the decomposition given by Ito's lemma. And it's not a coincidence that they match, otherwise Ito's lemma wouldn't be correct, right? If I run this again and again and again, I'm going to get tons of different paths, but Ito's lemma is going to be correct every single time in decomposing that differential into those two components. And we can just see this as we continue to simulate different paths of that function. It shouldn't be too difficult to grasp the idea that the differential of a function of a random variable is also itself a random variable. This goes back to the x squared example above with the normal distribution, because let's say I have a random variable, we know that means distribution of outcomes. I have a function of that random variable, that means again distribution of outcomes. Then I'm differentiating that function of a random variable. Well, if that function of a random variable doesn't have a deterministic outcome, then how could the differential? Just applying the derivative operator is going to make it non-random? Certainly not, right? So now I think we're ready to approach this idea of integrating over a random variable, because if the differential is going to be a random quantity, then surely the integral with respect to randomness will also be a random quantity. And surely it is. When we look at this, and this is an example here of an Ito integral, a stochastic integral, a random integral, if you like. Effectively, this is the cumulative effect of weighted randomness. And what I mean to say here is we can take a look at this stochastic integral in several components. So we have this time-dependent function of a process here. It doesn't even have to be of a process. It could just be of time, or, you know, there's other forms of this integral, like some sort of Volterra process where you have some sort of autocovariance kernel. But I'll digress from that for now. Really what we're looking at here is some sort of weighting of the Brownian motion. So let's think back to the Brownian motion process. In fact, I can even scroll up a little bit here. So what's happening is I have these Brownian increments, right? That's this noise here. The increments themselves, they're independent and they're governed by this normal distribution. To get the Brownian paths, I'm taking the cumulative sum. So it's actually very similar in construction, this stochastic integral, if we look at it as such, right? Because an integral is really just a continuous sum, right? That's really all we're dealing with. And that's given by the definition of the integral from traditional calculus that we saw above. So what are we looking at here? We're looking at this cumulative sum of Brownian increments weighted by this function. That's really all a stochastic integral is. And in this sense, what we have to realize is if it's going to be this cumulative sum of weighted Brownian increments, then clearly the outcome must also be random because those increments are random, right? Just as we said before, anything involving the Brownian motion is going to be involving some sort of distribution. So that's how we can think of this stochastic integral in these separate components. And the actual value associated with this integral for one sample path is itself going to be the weighted cumulative sum of the Brownian increments. If we're interested in the dynamics of the randomness, we could be interested in the distribution, we could be interested in mean, variance, things of that nature. We can also compute those statistics. But for now, I'll digress and we can focus on visualizing this idea of the stochastic integral. I think it's also important to note that just as in the traditional calculus sense where we can discretize the integral and simulate it numerically to approximate the value, we can certainly do that here as well. And you can actually take a look. This is one example of how we might do it. There are, again, many different schemes we can use. But this is one way of simulating a value for this integral. Again, very important. This integral is a distribution. So if I was to numerically simulate it, this would be one possible path for the integral. It's a distribution of possible outcomes. So when I go about simulating it, I'm not getting something that's approximating the solution. I'm getting a possible path, a possible sample from this integral density. So now I think we're ready to go about visualizing it since we understand all of these different components. And there's this really cool idea of lifting that we can use to understand this cumulative sum of weights, of essentially weighting the Brownian increments. And that's what we can see in this three-dimensional chart here. So if you take a look at this chart, I have time, I have Brownian motion, and I have weight. And it looks like there's a lot of funky stuff going on here, but bear with me. So what we have is we have a Brownian path, and I'm going to get rid of the other paths just so that we can start with a simple Brownian path. And this Brownian path is just the simple Brownian motion that we saw above. So the Brownian motion that we're seeing here, this red path here, it doesn't have any value on the z-axis. There's no weight, and it is equivalent to a path like this. Now you can see there's this surface. What does this surface represent? Well, the surface is actually representing this weight function. So in this example, I'm using just the value t. And if I use the value t, then I can create this surface in a three-dimensional space. And you'll see I have these red lines that are raising the path to this surface. And that's this lifted path here. This lifted path on the surface. So the stochastic integral is concerned with this lifted path. This lifted path represents the weight at each point in the Brownian motion being applied to the increment. And then we're just going to take the cumulative sum of those weighted increments. So it's quite an elegant visualization to understand what's happening in a single integral path. And we can actually go about visualizing now the integral value. You can see here, again, all of the processes are going to start at 0, and that's to be expected. And then it's going to accumulate according to the weight governed by this surface and the random increments in the Brownian path. Now, this is the Ito integral, stochastic integral, random integral value governed by this orange path, but that's not the one solution. If I run this again, I'm going to get a different path. If I run this again, I'm going to get a different path. Because again, we're dealing with randomness. So the integral itself is going to have an outcome that follows some sort of distribution because it is in fact a function of random variables. For those of us who are keen on integration, yeah, by the law of large numbers, I could just simulate a large number of Ito integral paths, take the mean, take the variance, take a look at a whole bunch of different statistics by the law of large numbers, and I will have some measures associated with that integral in a numerical capacity. Of course, they'll converge to the population measures, assuming I'm discretizing the integral correctly, but we're after analytical solutions if at all possible. And really, this is going to start to concern ourselves with the idea of a stochastic differential equation, particularly important in pricing where efficiency is necessary. So we can move on to this idea of solving stochastic integrals, and this is going to involve stochastic differential equations. So there's a general recipe that I've written out here. This isn't a video on stochastic differential equations. I'm certainly going to do one on SDEs in the future. But for now, a general recipe is to find some sort of candidate function, apply Ito's lemma, rearrange the terms and integrate, and then maybe you can find yourself a solution. Before we dive into solving this simple stochastic integral, discuss what we expect to see in the answer. So we know that the Ito integral is a random variable. It has to be. It's a function of a random variable, right? It's an operator on a function of a random variable, whatever you want to call it, however you want to call it. If I run this a billion times, I'm going to get a whole bunch of different paths, and the distribution, the statistics for the distribution will converge, so on and so forth. But if the outcome of the numerical simulation is a distribution, that is, this Ito integral is in fact a random quantity, then the solution to the Ito integral has to involve a random variable. It has to. Otherwise, we would be dealing with a deterministic quantity. So when we solve this integral, we're solving for the quantity that governs its distribution, which is a random quantity, a random variable, usually in terms of some sort of Brownian motion. So let's see this in action. This isn't a video on stochastic differential equations. I'm going to do one of those in the future. But the general recipe here, generate candidate function, apply Ito's lemma, rearrange, and integrate for a solution. We can do this with this very simple stochastic integral. What I'm going to do is I'm going to start by guessing this function, wt squared. So that's going to be my candidate function. I can apply Ito's lemma to find the differential. And I'm just going to go ahead and expand out this function using Ito's lemma. And then I'm going to take these partial derivatives. So I have this partial derivative here of the candidate function with respect to time. I have with respect to Brownian motion, and the second order with respect to Brownian motion. Again, that extra Ito correction term. If I partially differentiate this, operates just like traditional calculus in that sense. I get 0 because there's no time. I take the derivative with respect to Brownian motion. I get 2 times Brownian motion. And if I take the second partial derivative, then I just get 2. Can go ahead and plug these values in now. Plug those in for the differential. And I end up with this guy here. I end up with this for the value of the differential. It's very similar to the example that we did above in Ito's lemma. But now what I can do is I can integrate both sides of the equation. So I'm going to integrate this side of the equation, integrate this side of the equation. If I integrate the left side of the equation, I just get the candidate function. Remember, the integral undoes the derivative operator, so I'm just going to get the original function. And, you know, we also have this idea of the origin point, but that origin point is going to be 0. I'm just going to kind of table that for now. But I just mentioned it in case you were wondering where that term had went. Moreover, if I integrate the other side of the equation, I distribute the integral, then dt is just going to go to t, right? Just a very simple integral. Then I have this stochastic integral. That is what we're trying to solve for, isn't it? But now we have it in terms of these random quantities. So I can just subtract over time to this side of the equation, divide both sides by 2, and boom, that is my solution to the stochastic integral. But the stochastic integral, again, has to have randomness in its analytical solution because its solution is a distribution of outcomes. So we can see here that it does in fact involve a random quantity. It involves the original candidate function squared, less time, and everything is going to be scaled by this fraction 1/2. That is the analytical solution to this Ito integral. It is in terms of Brownian motion to be expected because the Ito integral itself is a function of randomness, so its solution must involve randomness. How important is an analytical solution for a stochastic integral? Well, it's kind of important and kind of not as well. Some integrals are going to be intractable and some may have analytical solutions, but in any case, we're going to be discretizing it anyway, right? So if this is the solution and I wanted to simulate this integral, then I need to discretize this anyway, right, with the computer. But I could also just discretize the original integral and simulate it numerically in the previous capacity that I had discussed here. So both should yield the same distribution because it's governed by the same stochastic integral, right? If I'm discretizing it correctly, as I did in that three-dimensional surface example, or I discretize this analytical solution, I should be generating from that same underlying distribution governed by that stochastic integral, and I certainly am. So that's what I've done here. I've numerically simulated the discretization of the integral itself using this scheme, the Euler-Maruyama scheme, and the analytical solution itself. And you can see here, as dt becomes arbitrarily small, the error decreases with the time steps and the solutions converge. So you can see here, there's this slight gap between the solutions. dt starts to become arbitrarily small until they are sufficiently overlapped. And that's because we expect either solution to produce the same sample quality from the underlying distribution. And it certainly does, as you can see in this convergence here and the decrease in the error rate for the increase in the sample size. This is exactly what we'd expect to see. But we need to separate this in our minds because the analytical solution is great, and in a pricing capacity, it's necessary because we need to calibrate to some sort of surface to extract parameters, and efficiency is important. So efficiency is certainly important, but in some cases it's intractable, so we need to simulate to be able to produce a path or produce statistics to find prices or parameters, whatever it is we're looking for. So we can see in either capacity, right, whether we're using the analytical solution or the numerical solution, we do draw from the same density, right? But again, there are going to be different implications, right? Because I can use this analytical formula here that we've solved for in a different equation, right? If I'm trying to come up with some sort of pricing model, I can now use that. If I'm using this setup here to govern the shocks or the dynamics of some sort of asset path, whatever, then I can use this now in some sort of subsequent equation. I can't necessarily do that here in an analytical capacity, right? Because I can do analytical work with this, but I can't necessarily do analytical work with this, but I certainly can discretize it, right? So in this case, this solution does exist, and I can use this in other equations, but sometimes it won't exist, and I'll just have to deal with the discretization, which we can see draws from the same underlying distribution anyway. So it doesn't matter from that sense of, you know, being able to produce sample paths or simulate prices or whatever. But in terms of efficiency and subsequent closed form pricing functionals, yeah, it's certainly going to matter quite a bit, right? We're going to want that analytical solution, but very rarely will that be the case that we actually have one. I've gotten some great comments in the past on this idea of Ito calculus versus, say, like Stratanovich calculus. Like, why bother with the Ito correction term in Ito's lemma if Stratanovich integration and the Stratanovich derivative for that matter doesn't concern itself with it? And that's because we, in pricing, care if the process we're dealing with is adapted to a filtration, if it's a martingale. And in Stratanovich calculus, we don't have a martingale. And very simply, if we take a look at this simulation from traditional calculus, the Ito calculus is effectively using the left endpoint of this rectangle, where the Stratanovich calculus is using the midpoint, so it's anticipatory in that capacity. So it's not itself going to be a martingale. So remember, whether you're dealing with an Ito integral or a Stratanovich integral, it's going to be random, right? Because you're dealing with a function of randomness. But whether or not that randomness is in fact a martingale, now that is where the question lies. So the Ito calculus does ensure, and even if you discretize it in either of the capacities we have above here, that it is still a martingale. But in the Stratanovich sense, it will not be. And that has major implications in pricing. But those are videos for another day. I want to talk about risk neutral pricing. I want to talk about stochastic differential equations, quadrature, martingales, so on and so forth. That'll be stuff to look forward to. In itself, stochastic integration is tricky, and that's because we have a lot of different ideas floating around, right? The integral from traditional calculus, we want to cling to that because that's what we know, that's what we understand. Area under the curve, the antiderivative. But when we bring in randomness, we're starting to deal with distributions, right? And the stochastic integral itself has to be viewed as a distribution, but we kind of took a look at each of the components and we said, okay, hey, we're dealing with this idea of a cumulative sum, really, that's all the integral is, of these Brownian increments, which are very well defined, and those Brownian increments are just weighted by some sort of function. That's really all a stochastic integral is, and that's going to yield some sort of set of sample paths and, of course, a distribution. And that's going to do it for this video on Ito integration, stochastic, random integration, whatever the heck you want to call it. It has been quite a lot of fun to make these videos on Ito's lemma and now Ito integration. Very excited to focus on those other topics in the future, particularly as they pertain to pricing. Other than that, if you enjoy topics like this, if you want to see more like this in the future, more Jupyter notebooks structured in this capacity on the Quant Guild library, please, leave a comment below, like, subscribe. It helps me out a lot. Check out quantguild.com. Check out the resources below to help support the channel in any capacity. I greatly appreciate it. Other than that, thank you so much for watching, and I will see you in the next video.